All right, we are on the fourth video now for chapter 14, looking at equilibrium. We have identified how to write equilibrium constant for the equilibrium expression. And we know equilibrium occurs when reactants rate and the forward rate become equal to each other. All right, so now that we have a system in equilibrium, what will happen if you do something to disturb it? And that's what we're going to be looking at in this video. All right, here we go. Le Chatelier's principle states that when you add some type of stress to the system, okay, so you're at equilibrium and you do something to disrupt it, the system will now want to shift in whatever direction that will minimize that effect. All right, what does that mean then? You're in equilibrium, then you do something to stress. Now, what are these stresses that we're talking about to the system? One thing you could do to stress it would be to remove or add some reactant or product. You could also change the volume of the system. Okay, when you look at the reaction here, we have N2 and H2 gives us NH3, all right, so reaction for the synthesis of ammonia. What's going on as far as if we have the system in equilibrium, and now let's try to add a reactant. All right, so let's look here, and we're going to then say, well, let's add a reactant. Well, the system will want to shift to now get rid of that. And how would it shift? Well, the reaction will get rid of some reactant if you go this way. It will use up that reactant and start making more product. So if a system is stressed by the addition of a reactant, it will go towards the product side. Okay, so the rate of the forward rate might become a little bit faster now, and you might make more product, and then again an equilibrium will be established. All right, same thing with removal of something. So if you take away a product, so let's say we have this reaction, we've reached equilibrium, we remove the NH3 that was produced, well, the reaction will then shift to make more of whatever was removed. So this way would again shift to the right-hand side. How about change in volume? Okay, now volume and pressure are related. Okay, there's an inverse relationship if you remember back to the chapter about gas laws. And so if you decrease the volume of a system, what happens to the pressure of that system? Well, since it's inverse, if you decrease the volume, the pressure would go up, okay? So let's say you did something to change the volume by decreasing it, which thereby you now increase the pressure. What would happen to this system, and how would you be able to figure that out? One thing you want to notice is the reactants and the products. What phase are they in? Do you see that everything here is in the gas phase? All right, and so when we're thinking about the pressure going up, well, that's the pressure of the gases here in this system. And now if you've increased it, it's going to want to shift to now decrease the pressure, right? If you increase the pressure, the system will want to shift to minimize that stress, so it will decrease the pressure. Now, can you answer that question yet? Which way would this shift if you increase the pressure? Maybe if I did this would help you. I'm going to add up the moles of gas on the reactant side, and I'll say there's 1 mole of N2 and 3 moles of H2. I'm pulling those numbers from the valence equation, and I'm going to say that on the reactant side there are 4 moles of gas. On the product side, it's just NH3. The coefficient in front of that is 2, so there's 2 moles of gas. Now, if I just decrease the volume of the system, which thereby increase the pressure of this system will want to shift in a direction to then decrease that pressure. Which way would it shift? To the reactant side or the product side, which would then cause a decrease in the pressure? You should be able to see that since there's only 2 moles on the product side, if we shifted to make more product, now you'll have more moles of NH3, less moles of the other ones. You will then thereby have decreased that pressure change. Okay, so change in volume, you want to think about how many moles of gas are on both sides of the reactants and products. They could be equal to each other, and so then a change in volume and a change in pressure would have 0 result on the reaction. But if it's not even, okay, if you want to increase pressure, it will shift to then decrease the pressure. All right, we can also look at change in temperature and how that affects. And you're going to have to remember things about endo and exothermic reactions and how to make this work. Now you see a change in enthalpy. Okay, so I have an H there for enthalpy, which is a change in heat. Heat there. And I'm just going to write the word enthalpy in there. And we can see that this value here, and we've looked at change in energy for reactions, and we can see that this is a negative value for this reaction. And that negative value indicates to us that this is what type of reaction. This is endo or exothermic. That negative value, you should remember, means exothermic. And that means that overall the energy is given off by this reaction. And you can see that I added plus heat here. So for an exothermic reaction, you want to think of heat as a product. And what does that mean? Well, if this system now has a change in temperature, you want to think of it reacting just like the other reactants and products, so that it would shift to then minimize that stress. So let's say heat is removed from this system. We have N2 plus H2 reacting, forming ammonia, and heat's given off in this reaction. If you remove some of the heat from this reaction will shift to make more heat. And which way is that? It will go towards the product side. All right, so if you have an endothermic, that is when you would have a positive change in heat or a positive enthalpy for the reaction. You want to think of adding the heat to the reactant side. All right, let's do another example just to make sure we can get this all figured out. Here is a reaction we've been looking at. The textbook, the Russo textbook, has this reaction with this picture. So just to bring that to your attention, we have SO2 plus O2. Reaction gives us SO3. All right, initially this system was in equilibrium. By looking at this first box right here, can you tell this is in equilibrium? You should be able to say yes, it's in equilibrium because the rate forward equals the rate reverse. The arrows are pointing both straight up. The equal rates, equilibrium. Does that mean that the reactants and product concentration is equal? Absolutely not. That's not the definition of equilibrium. Equilibrium definition is all about the rates being equal. Since the products are greater at equilibrium than the reactants, we would say that this reaction lies to the right, and it's very product favored. Okay, that means the equilibrium constant should be large for this reaction. All right, so we're at equilibrium. We're going to do something to the system. We're going to disturb it, stress it out, and then we're going to see what will happen. All right, so here's what the first thing is. Remove all of the SO2 and O2. All right, so if you take all of the reactants, get them out of there, what will this system do? Well, the forward rate just went down to nothing because you have no reactants to go and make products. All right, and so then the reverse rate has to increase a little bit to start making some reactants back. And then over time, a new equilibrium will be established. And again, you will have equal rates. You will be in equilibrium. Is the rates going to be equal to the initial equilibrium rates? Possibly, but it doesn't have to be. As long as they're equal, you have now reached a new equilibrium. Here's another thing to note. The concentration at equilibrium of the reactants and the concentration of the products at equilibrium are not necessarily going to be equal to the initial equilibrium concentrations. But K equilibrium will still be the same. Okay, this is your products over reactants. All right, so that will still stay the same. Okay, so the rate, and you can see that they both have gone down a little bit. Here, this was 1.8, now this has gone down. This was initially at 0.2, then it went to 0, and then some of it came back. All right, so let's see, that was if all the SO2 and O2 were removed. Let's say we're going to do a different thing to stress the system. Can we predict which way it will shift? For this case, backtrack a little bit. Once we removed all of the SO2 and O2, this system shifted to the right to make more, it shifted to the left to make more reactants. So we shifted left. All right, well, what will happen if we add SO3 to the system? So here we go, new picture. We have the system's in equilibrium. We're going to add SO3. So we're adding a product. It's going to want to shift to minimize that. So instead of now making more and more product, it's going to shift the opposite direction to get rid of some of that product. All right, so we are going to shift left to remove some of that product that was added. All right, how about if we increase the pressure on the system? Which way would this reaction shift? So if we're increasing the pressure, that would also be decreasing the volume. That's one way of doing it. Which way would we shift here? All right, we have to look at what we have going on with this reaction. How many moles of gas are on both sides? So on the reactant side, we have a 2 plus 1, so 3 moles of gas. And then on the product side, there are 2 moles of gas. And if you are increasing the pressure, the system will want to shift to either to the right or to the left to decrease pressure. Is there more pressure on the reactant or on the product side? Well, since there's 3 moles of gas on the product side, if you have more product, you're going to have a higher pressure. So this reaction will shift to minimize the pressure, and it will shift to the product side. Shift to the product side, which is the right. All right, and then last one here, if you are going to remove some heat from the system, which way would the reaction shift? Can you answer that right now? If you're thinking about it, you might be thinking, well, she has to tell us some other information first, right? In order to answer a question about if heat is going to be added or removed, you need to know if the system is exothermic or endothermic. So let me give you that. The change in energy for this reaction, or the change in enthalpy, is minus 197 kilojoules per mole. All right, so based on that, now can you tell me if we remove heat, which way would we shift? Well, since this is exothermic, I want to think of heat as a product. Okay, heat is being given off. And so now if we're removing heat, so if heat is being removed, this reaction is going to shift in order to make more heat, and the heat is on the product side, so we're going to be shifting to the right again. All right, students often find these kind of fun to kind of figure out. Take your system, figure out if something's being added, pressure changing, heat changing, and then how the system will respond. So be sure to do some more practice with these, but that will be it for this video.